My name is Hrishikesh Ghodke, and I'm here with my colleague Ronak Trivedi. Unfortunately, our third partner was not able to fly down from UK, but we are here to support him. Uh, so I would like to start with by asking a question. Have you ever wondered how or what your network packet looks like when it enters AWS network? how how secure it is, or have you ever thought of how you can set observability around it? Well, if not, that's fine. You can learn what we did and try to implement. So we did exact things to uh, excuse me. We did build our secure network connectivity and observability. Uh, Today we are going to talk about the AWS network inspection. That's an overview. Some automation that we did around VPC migration into inspection. Okay. So our agenda for today is we are going to talk around AWS centralized inspection. We are trying to give you an overview of how it looks like. Automation around our VPC migration from non-inspection to inspection pattern. Our packet drop monitoring tool, which is an observability tool, and firewall policy automation. I would like to invite Ronak to give an overview of our past and connect.
Yep. So traditionally, I think many are familiar with a network-centric network security architecture model, where you might have your application tier segmented into one network zone, your database tier into another zone, and you have firewalls protecting those zones. So that was kind of like the past for us at Discover. We wanted to move into a more granular segmentation, such that I think a lot of us in this room are familiar with vulnerabilities, exploits, even external hackers trying to get into our networks. When with a network centric model, when they get into that zone, they can move east west, they can move laterally with no firewall in between those applications. We wanted to essentially enhance our security in the cloud by moving to an application centric architecture, which essentially will decrease our blast radius when we get hit with vulnerabilities, attackers getting into that application. Sure, fine, they can get into that one application, but if we have firewalls protecting around that application, they're stuck there. They won't be able to move laterally how they would be in a network centric architecture. So that kind of lays the ground for why we moved to the transit gateway and put VM firewalls into the cloud to inspect all traffic between VPCs.
So on screen on your left, you see spoke VPCs which are attached to a transit gateway which is in center. You can see security VPC on your right, where we have our gateway load balancers and firewall behind those. So let's say a packet is originating from spoke VPC 1 and is destined to go to spoke VPC 2. The traffic path for it will look like this. It will be forwarded via transit gateway firewalls within security VPC and back to transit gateway and to its destination. Here the firewall will decide if it wants to drop or allow a packet depending on the firewall policies that we add. If now a packet is originating from spoke VPC 2, the path will look similar, but this time it will need a separate set of firewall policies to allow this packet. So this was an overview of inspection, but what we have at Discover is more complex. We have 200 plus VPCs, which has connectivity within same region and within different regions. So as that complex pattern, we wanted to start migrating our VPCs from non-inspection to inspection. And that led us to think about automation around it. So what you see on screen, we are talking about two regions where you can see certain VPCs are associated to transit gateway route table. That's where we are segmenting our VPC traffic. We chose to migrate one VPC at a time to minimize the impact during our migration from non-inspection to inspection pattern. So there are certain steps that need to happen in the process, and that too in parallel, to avoid any asynchronous routing. That's where we thought of building a CI/CD pipeline. This pipeline will help us choose which VPC to migrate, which all route tables to update with certain routes to avoid any asynchronous routing during the process. And it will also help us choose which transit gateway association to choose. So in short, with a single click of button, we were able to migrate over 200 VPCs, that too in a record-breaking time. Next is Packet Drop Monitor, which is an observability tool that is a homegrown solution which looks into or which analyze traffic logs to send real-time notification. This tool sends real-time notifications to the end user. So for example, if my colleague David has an EC2 instance in Spoke VPC 1, if you remember from the past slide, and if he wants to reach to a destination which is in Spoke VPC 2, and for some reason, a packet is dropped at a certain firewall location. We have a complex connectivity, as I said. There are multiple firewalls deployed across multiple regions and environment too. So David will get notified for his packet drop with a location, so he can act fast and accurately. This solution is also AWS native, where we have used native resources which are proven to be highly available and scalable. It's a cost-efficient tool which has saved money to our company by sending traffic logs over secured AWS backbone network versus sending it over transit gateway. Let's take a deeper dive and see how this tool works. So on your left, you can see security VPC, where we have our firewalls, which send traffic to AWS vector instance, which will basically manipulate and filter the logs. Vector then sends or forward those logs to CloudWatch log group using CloudWatch agent within an instance. This is the final format that we are capturing, where we are capturing start time, source IPs, source port, destination ports, and destination IPs, along with action and device name. Device name here is crucial. As I said, there are multiple locations, and that will give us an important information on which location the packet was dropped. The CloudWatch log group has a Kinesis subscription, which is also a trigger on our Lambda. So as soon as a log is sent to a CloudWatch log group, our Lambda will get that event. As soon as the event is received, Lambda adds an entry to our DynamoDB database, which is also a unique entry it adds with a retention time. When an entry is added to a DynamoDB table, Lambda then queries our public cloud API, which is a metadata for our entire AWS environment. So depending on the source IP, it is able to pull the contact information for the end user. So it pulls based on tags, or if there is a tag missing with the contact information, it pulls the organization email address based on that, it sends out email notifications. And that's what our send email Lambda function does, to send out email notifications to the end user. The email notification will look something like this, where we are trying to inform the end user about their packet that was dropped so that they can act faster if that traffic was intended and if that needs to be allowed on over the firewall. So this tool has helped us a lot during our migrations, as well as it is helping us now to reduce the incident response time. So any user who is unfamiliar with any observability tool can just reach into their email address or emails, try to search by a source IP, and use the information to create firewall policies. I will invite next Ronak to talk more about firewall and firewall policies.
Yep. So initially, I talked about kind of the first journey of how this initiative came about, moving to the transit gateway with firewalls in the cloud and routing all of our VPC to VPC traffic to that. So that was kind of the first journey to this story. But the second journey is, okay, now that we have that plan, how are we going to support this in a secure way, in an automatable way, such that we're able to essentially service hundreds of application teams in a standardized way? And that journey for us started with a term that we kind of coined at Discover called access maps. So first of all, we'll talk about what is an access map. Essentially, it is a repository that's owned by application teams, which will track their firewall rules, but not only their firewall rules, their security group rules as well. So why access maps? We wanted to shift left with ownership, meaning traditionally network security teams would store all of the policy for all of the application teams, say in a centralized SharePoint drive. And it'll be a bunch of Excel sheets, each one linked to an application team. But with Excel sheets, they're tedious to maintain. You can't do input validation. And how are you going to implement into the cloud or into firewalls based off an Excel sheet, right? So that's why we had to switch to what we call access maps. And the way that we have it structured is in JSON, but it really could be structured in any programming language such that we can take in requests in JSON and formulate those requests into whether it be Terraform to create SG groups or our firewall manager to create actual firewall policy. And by doing so, we've increased our automation capabilities. So actual engineers and operation members aren't going in and implementing this access manually. They're actually just going off of the requests that are formed by our automation. So you can see here kind of how these are structured, and ours are obviously more complex. This is just a general idea. So you see you have address group 1 with some IP address, and then for example, we have security group 1, and we'll differentiate all the security groups in the access map based on account number and VPC. And ideally, that security group will be the real security group name that is present in AWS. And then you have the policy. So using those objects to actually create rules for whether it be in AWS or the firewall itself. So now that we have our access maps, how do we automate the implementation of all this access? So first, let's be honest, application teams, sure, they own their applications, but do they know all of their IP addresses associated with all their services, all their servers and databases? Probably not. So what the AWS team did, Rishi's team, they provided the application teams with VPC flow logs, all of the traffic that went through their account. And because there's now firewalls in the cloud, that traffic between VPCs was initially handled between VPC peers. Now we'll need firewall rules for each one of those connections between VPCs. So with all of that influx in firewall rules, we're going to need automation to help the application teams, so that way they don't miss submitting firewall rules. So when we go to the transit gateway, they're not seeing traffic drops because, hey, they forgot to submit a firewall rule for a pattern that they thought they had covered but didn't. So what we did was we created automation to sift through all of the flow logs and sift through their access map that I covered on the previous slide and ensure that they have rules that cover each one of those entries in their flow logs. So once we've gathered all of the firewall rules that we need submitted so that they don't see any traffic drops and it's kind of a seamless migration that they don't even really realize happened, but really a lot of work went in the background. So that brings us to the automated staging and implementation of this policy. As you can see in the diagram, we use ServiceNow as our ticketing system. What users will do, application teams will do, is they'll submit their access request through ServiceNow, and that will be right away sent to our automation platform and linted and validated and ensured that, hey, they didn't fat finger an IP address. Hey, they're not requesting an insecure port. It's essentially standardized to our guidelines. And if it's not, our automation platform will send it back to them and let them know what they need to do to change that until it's at a good point, to where then an operations team member can look at that request, press approve, and that's all they need to do. They don't need to write up an implementation plan. They don't need to go back and forth with the application team saying, hey, are you sure you don't want this CIDR? Everything is handled by the automation. All they need to do is approve or deny the request. Once they approve the request, it gets sent back to our automation platform and it's automated. So one thing I didn't mention was application teams can either use the security groups that are protecting their resources or the CIDRs, the IP addresses behind those security groups. A lot of times application teams might not know the CIDRs, or they're dynamic. They're constantly changing, so it's better to just use the security group. And our firewall manager has an AWS plugin that will translate the security groups dynamically to the current IP behind them. So whether they submit IP addresses or security groups, our automation platform will go into Terraform, request the SG changes required, implement those into AWS. It will go into our firewall manager and place those rules onto the firewall automatically, such that operations team members no longer need manual intervention, which reduces risk and time to go live. And as you can see here, we have the GitHub icon, and this goes back to my previous slide where we wanted to shift left ownership, right? So we had all of the access stored in Excel sheets previously, but with GitHub repos, we can assign a repo for each application team that they own access to, and they own the roles that are tied to those repos. So if anybody else needs access to that repo to see the policy for that application team is the one that grants access to that. It's no longer network security reliable for owning their access. So as you can see in the diagram, I explained going from a request, getting approved by the operations team, and then eventually implemented onto the firewalls. And that is the full flow of how we add firewall rules automatically. Rishi?